Yeah, look. So quick recap of this chapter I'm giving you. Okay, of the ray optics. We have already completed this chapter. So the first concept is refractive index. First, we define the absolute refractive index, mu m, refractive index of a medium. It is equal to speed of light in air to the speed of light in that medium. And if we are talking about the relative refractive index of 2 with respect to 1, it will be equal to V1 by V2, or refractive index of 1 with respect to 2, it will be equal to V2 by V1. Then we have this second formula you can see here, the relationship of refractive index with the wavelength. And wavelength is related with the color. So refractive index is equal to A plus B by lambda square. Okay. It is extended, this formula is extended further, but mu is equal to A plus B by lambda square. This is known as Cauchy formula. Here you can see A and B are constant, and refractive index is inversely proportional to wavelength square. Okay. So this is the dependence of refractive index with respect to this speed of light. Now third is Snell's law, laws of refraction we have seen. So in Snell's law, what we have seen? Okay, this formula you need to remember as ratio of sine of angle of incidence to the sine of angle of refraction. It is always constant for a pair of media and for a given wavelength of light. Sine I upon sine R, basically it will give you the speed of light in medium 1 from where the light is coming, and divided by V2. V2 means the speed of light in the medium to which the light is going or traveling. Okay, this can also be written. Here you can see refractive index is inversely proportional to the speed of light in that medium. So it will be equal to mu2 by mu1 in terms of relative refractive index. Or the same can be written as refractive index of 2 with respect to 1. That will be always constant for a pair of medium. This is the actual form of Snell's law of refraction. Okay, so this is Snell's first law, and second is the incident ray, refracted ray, and the normal at the point of incidence all lie in the same way. The next we will see the apparent depth and real depth. We have seen the refraction of light through plane interface. First we have seen refraction of light through plane interface. Through plane interface. In this topic or in this category, basically, first we have seen apparent depth and real depth, relationship between apparent depth and real depth. So this is the relationship. Real depth divided by apparent depth it is equal to mu2 by mu1, or basically mu1 by mu2 you can write down mu1 by mu2, or basically you can write down it is refractive index of 1 with respect to 2. What is mu1? Mu1 is the refractive index. You must remember these points. Refractive index of the medium where object is placed. Okay, where object is placed. Okay, and mu2, or basically you can say mu1 is the refractive index of the medium from where the light is coming, and mu2 is equal to refractive index of the medium where observer is placed, or where observer is, or from where the observer is observing. Okay, or to which, or the medium to which the light is going. Okay, observer basically. So you need to remember, because in the book directly it is written mu. Okay, but this is the actual form of the apparent depth, relationship between apparent depth and real depth. This is the first formula you must remember. This is your first formula. Here in case of apparent depth and real depth, basically this we can take as A. And second is the shift. Okay, what is the shift in the position of the object due to the refraction of light? So shift is equal to basically difference of these two, real depth minus apparent depth. If real depth is greater than apparent depth, then we can take this value. Sometimes what happens, apparent depth is more. I have already with the help of the ray diagram. So you can take the mod sum. Real depth minus apparent depth, that will give you the shift in the position of the object. Okay. Now next we will see the refraction of light, or we have already seen basically the refraction of light through rectangular glass. Okay. Refraction of light through rectangular glass slab. So lateral shift, the expression of lateral shift we have seen when light travels from suppose air medium or from a medium to a rectangular glass slab, there will be laterally shift in the path of the light ray. And how much lateral shift will be there? This lateral shift D, if lateral shift is denoted by D we have calculated. It is equal to T into sine of I minus R divided by cos R. Okay, this formula we have derived. And the factors on which the lateral shift will depend, we have already seen. Lateral shift depends upon the thickness of the glass slab, obviously the angle of incidence, refractive index of the material of the glass, and obviously the color of the light used. All these things I have explained. So this is the lateral shift, expression of lateral shift. Then we have seen the refraction of light through a glass prism. Refraction of light through a glass prism. Okay, or through a prism we have seen. So refraction of light through a glass prism, what we have seen? We have seen this formula basically. First we have seen the angle of deviation, delta. So angle of deviation we have calculated, because light will deviate from its actual path when light travels from one medium to other medium, optical medium to other optical medium. So angle of deviation, first we have calculated delta. Delta is equal to I plus E angle of incidence plus angle of emergence minus R1 plus R2, 2 angle of reflection. R1 plus R2 we have seen it is equal to angle of prism. So it will be also equals to I plus E minus R1 plus R2, it will become A. This we have already calculated. So this is the first formula that we have obtained in angle, refraction of light through a glass prism. Angle of deviation we have calculated. Next, we have calculated the condition for minimum deviation. When delta will become delta minimum, when you will get minimum value of angle of deviation. When we will get? We will get when I equals to R, angle of incidence equals to angle of refraction. It's the, sorry, angle of emergence. When you will get I is equal to E and R1 is equal to R2, then you will get the minimum deviation. Then you will get the value of minimum deviation or angle of minimum deviation you will get through the glass prism. And we have obtained this formula. Okay. This formula we have obtained sine of delta minimum plus A by 2, okay, divided by sine of A by 2, it is equal to mu 2 by mu 1. Again, you remember mu 2 is the refractive index. Mu 2 is the refractive index of prism, material of prism. And mu 1 is the refractive index of the surrounding or the medium in which the glass prism is placed. So this is the formula. These are the terms you must remember. Directly we cannot write down mu here. Okay. Here you can see this formula is the actual formula. Relationship of angle of minimum deviation to the refractive index of material of prism. Then we have seen this third formula also for the thin prism. So for thin prism, this sine theta will become theta. So this value we can apply for thin prism. For thin prism, this delta minimum will become mu 2 by mu 1 minus 1 into A. This is the formula we have obtained, isn't it? Yeah. So up to this point, we have seen the refraction of light through this plane interface. After that, we have seen the refraction of light through the spherical surface also. You can see. If you are finding any difficulty, you can ask me. Okay. Please tell me in the chat box. No. Okay.